Thank you, Aaron. So our next speaker is Ryan from CSIRO from Australia, and he will be also in the Rising Stars session. Thank you, Ryan, for being with us with so early hours in Australia. So floor is yours, and please start.
Good morning, everyone. I hope everyone can hear me. Slash evening over there. Today I'm going to give a brief overview, very brief overview of the last 8-ish years of my career in CSIRO, and my focus on legged robotics. So some of you, or most of you, might know that we at CSIRO focused our research around multi-legged robots, especially more than quadrupeds, so more Hexapod robots was our focus. And we really try to push these robots out into the field as fast as we can to really get that experience and learn upon each iteration of our robots. So, I think I'm up to 13 or 14 different robots at this point in time, all for different jobs. So really quickly, the overview, we chose Hexapod robots as quite a simple platform, relatively simple platform, and that from a dynamic standpoint, they can be statically stable for a long time. You can use very simple gates, to the point of putting sine waves through the motors, and they still locomote. But obviously, this doesn't cut it. You need to actually control them. And one of the things that we really focus on is this ability to deal with uncertainty. And uncertainty, is something that we all face as roboticists. So Hexapods kind of gave us that by default. We focused on mostly bespoke tasks for the robots, and we researched the functionalities that we could achieve with these robots. They kind of afforded us this ability to do that, although most newer quadrupeds now can afford you this as well. So it's nice to see that coming through. And iteratively we built upon most functions. So really, it started out early 2014 or 2013. We got asked to put a robot inside a plane wing to do an inspection task during manufacturing. This problem isn't easy. Plane wings are extremely complex environment and very sensitive. So we really wanted to explore the use of legs and their ability to explore these environments. But the off-the-shelf robots really weren't up to speed at that time. They were very, as I said before, very simple. And they were essentially the same as putting a track robot inside of a wing. They were very clunky and they just hit things. So we started building upon this and created our own robots. And we created a ROS-based platform because we really quickly saw that we had to start building upon these to add functions, footfall planning, different gates, different everything around it. And here are 2 examples of those style of robots. So early days was over to the right, a robot that could unfold and expand inside a wing. And then down the bottom is our latest, I guess. And it's a robot that we can really throw into any situation. It's kind of coming into its own as an educational robot. They're pretty solid platforms for being able to do different experiments. So to extend upon this, we really started using multi-degree of freedom, over-actuate these things. They're already over-actuated, but we decided to look into what we could take advantage of if each leg had 5 degrees of freedom or 6 degrees of freedom. Can we do manipulation with one or two of the legs as the robots there? Can they deal with extreme terrains? Can we detect their footfalls? Do we have to? And what stance styles can we use? So, this again is pretty quick overview. So, but we started looking into two of the things that I can highlight is we started looking into mammalian gates. So classically, we stand in an insectoid gait where the legs are out, whereas a quadruped would stand in a mammalian gait where the legs are underneath it. And over to the right here, we have a hexapod, these over-actuated hexapods, able to reconfigure into a mammalian gait. And we're exploring whether this style of mammalian gait would give you more speed, or B, be able to, it makes sense to be able to suck your legs in and become a smaller platform to be able to go through smaller apertures in the environment. And we were interested in whether it was more locomotively efficient. It all seemed to come out in the noise. I believe that this wasn't terribly more efficient. I just did give you that ability to walk in a different stance. And then more excitingly and more along the lines of what we think robots are good for like this is the ability to step back and have a really sure-footed stance and then be able to scan and move things in your environment. So this mobile manipulation and the ability for the robot to actually achieve a task in its environment, yes, this is a simple one, but we can step back again on four legs and use both our manipulators to manipulate something in the environment. So this, again, this is something that we built on and built into our systems, built into our platforms, and is a function that most of our robots are able to achieve. During this time, I got to explore a bit of design space with the late Dr. Alberto Elfers, and we were really interested in creating what we termed an ultralight robot, where we could build something very large, human scale, that would weigh very little relative to its size. If you go up linearly in size, your mass goes up in the cube. So we were trying to beat that rule. And essentially, what we came up against was the flexibility of a robot, kind of versus this controllability. How much flex can you build into a system and still remain controllable and achieve the task of locomotion in unknown environments? These robots were proprioceptively walking. They were slow at the time, as we had a lot of problems to deal with. But the ultimate goal of these style of platforms was to be able to walk in forests. We really wanted to always be in an unstructured terrain. So, most of you might have seen this work before. This is again, these functionalities that we built in with Max all ended up in our controllers. The body has to do a lot of work to maintain stability, but all of this was still in a quasi-static realm. We were using, a fair few static tricks to be able to deal with the flexibility. And we started then looking into how can we dynamically control this and use it as as the robot sways, use its swaying energy to enhance its movement. Although bandwidth of actuation really was our problem when it came to being able to capture that motion, especially with different terrains. But as you can see, it can perform some pretty useful tasks. It can walk over some pretty decent objects, and it's a clear outline of how flexible the system is. And yeah, although again, still slow, needs a lot of work to speed it up. So to continue along, during this, we continued. We had many variants of different robots, and adhesion for inspection tasks came up as a very popular pull from industry. So we really started to take this seriously, and we really do think this is a very good part of the market to hit, although it's still a very unsolved problem. Adhesion seems to have its problems. So our colleague Tertha gave a talk earlier, but again, the video in the bottom left here, this robot is searching for footholds and testing every foothold as it goes along. There is no external sensing or localization on this robot, and the idea there is that we can end up going continuously on a surface, essentially, without needing to have a whole global map, or if things go wrong proprioceptively or at least locally to the robot, we can still get home safely. In the middle here, you can see our latest version of Magneto. It can carry a pretty significant payload as it achieves its climbing up a vertical structure. Yeah, it's quite an interesting robot. And really, one of the last final things there is the push for industrial inspection was we really had to interface with the environment that we were asked to climb. They wanted to put an ultrasonic sensor on, and there's to measure the thickness of the steel of the structure, and there is no other way to do it. So, legged robots are inherently already in touching the environment, so this robot is able to grasp the environment and place that sensor for the period of time reliably. Not going. So basically what I'm getting to here is that the CSIRO high-level controller, as it's been coined in CSIRO, we love naming things, we're pretty terrible at it. But it's an open source project now. You can go into GitHub, you can load this onto any robot. I believe it works for quadrupeds as well. Obviously it works for Magneto. It's very flexible. We used this earlier in the days where it goes on all of our platforms, multi-degree of freedom, high degree of freedom, or down to 18 degrees of freedom, or 3 degrees of freedom per leg. All of the functions, manipulation using our legs, single or double legs, is built into it, and we strive to support any of the community's kind of features or bugs that arrive. But as it's been tested on many platforms at work, we found that it's quite successful to be deployed amongst community that's started to uptake this, especially in Hexapod. But continuing on from that, forgot about my own slides. We took this, one of the next progressions was we wanted to deploy a robot in the Amazon rainforest. One of the things that we really faced against going into the Amazon was the ability for 1 or 2 people to deploy a robot remotely. We were in the middle of the Amazon. There wasn't any support, there was no internet. So we developed the Amazon robot. Again, we love naming things. And this robot was to be deployed in the rainforest. I self-deployed it. It was autonomous, albeit quite slow because of some controller problems and some timing deadlines, but it proprioceptively picked its footholds and slowly climbed its way through the forest. We saw this as an extension upon our sensor network that was already built in the Amazon rainforest. We were finding areas of interest with that, and the ultimate vision was to be able to deploy a robot with higher value payload to those places to be able to capture what was happening there in the rainforest. So from that learning, we quite quickly moved into the DARPA Subterranean Challenge, and we spec'd up, in the early days of the Subterranean Challenge, we were presented with quite difficult terrain. And so we wanted to extend what we had, these quasi-static robots that proprioceptively we could move around, into a dynamic hexapod that could be, would be able to increase the speed over ground during competition. So Bruce was designed and built in a year. We had a brand new architecture for control, and included dynamics and joint control, torque control, series elastic actuators. We went through about 5 iterations of legs in a year, and then it did deploy into the subterranean environment, although it did break gracefully, I must say, when it got into the tunnel. But yeah, so one of the big things is this bottom right clip here, where you can, grass is something that we're starting to learn is a very, very tricky thing for legged robots. So yeah, just being able to plow through it and keep your static stability high, or your stability high with that big contact patch of the tripod gate was really our aim, and we'd like to think that it really paid off for us in this scenario. So, we built upon our simulation environment and, all the usual whole body control things. We have our own Locomotion Engine that changes, body trajectories into foot trajectories in a very smooth way. And then that's handed down to a whole body controller of varying complexity, all the way from just simple impedance control per leg to force control at the foot. So you can see that off to the bottom right there. And it does show in sim and in the real world the ability to deal with these unknown undulating terrains and remains stable. And so this is a little bit of the development of Bruce. Within a year we went from 0.1 in the lab out to 0.7 meters a second. Our goal was to get to about 1.2 meters per second or 1 meter a second during competition. Although I must say that competition proved to be in the domain of the track robots, where they're fast and brutal, and more along the lines of autonomy and groups of team. So Bruce was shelved from the subterranean environment, and the work and the controllers are being continued by students in our lab currently, and we hope to be able to find an application for Bruce more suited, more bespoke. So I just wanted to finish up with some of the learnings, although this isn't extensive. What we're really chasing down is sure-footed tasks, somewhere where static stability or that large support polygon can really give it an advantage, and we find that in extreme environments. We want to push it out into climbing hills or subterranean environments where stopes start to. We want to get robots into stopes and unknown environments. But one of the big things is there was a huge effort in robustness into building new hardware within the lab. So we're starting to see more and more new actuation become available on the market, and this seems to be able to turn the tide of being able to build a robust system. So hopefully in the coming years we'll be able to build bespoke systems again that are able to achieve some of these goals that we want. One of the big learnings is that it's not a Lego system. You don't just bolt actuators together in a row to create dynamic systems. A lot of you guys would understand this. It's a system level thing. Each actuator needs to be suited to its task. One of the big areas that I'm very interested in is mass offset. So can we use parallel springs in these systems to offset that, annoying thing where we have to hold our mass up against gravity? And morphology really does matter. Rectilinear systems, especially in hexapods, doesn't seem to be the way to go. As an asymmetric circular robot is actually quite an advantageous thing when it comes to locomoting, as you've got homogeneous movement. And proprioceptive walking is really something that we want to focus on and be fast at, relatively fast, I should say. I believe quadrupeds can do it as well, but having 3 down and 3 up is quite fast. So thanks again. So my talk was very quick and covered a lot of things, and I'm happy to answer questions.
Okay, thank you very much, Ryan. We have one question from Dimitrios.
Sure.
So with your experience, what do you win with 6 legs over 4 legs in rough terrain or in general?
We were starting to see a win with rough terrain, traversability and speed. I bring this down to when quadrupeds, sorry, I should say we have quadrupeds now. When you go back to a tripod game, you go 1 foot at a time. That really slows down the platform. That we are always having 3 feet on the ground gave you a huge contact patch. And funnily enough, you can think of a hexapod in that mode as a bipedal robot. It's actually 2 large footprints that are overlapping that land. So that's where we were starting to see it. And that, again, that proprioceptive ability to absorb uncertainty was huge. But we came up against robustness as our big problem there.
Sorry, Christoph, can I
Yes,
elaborate?
yes,
Yeah,
during the DARPA challenge, did you face any failures in the hardware due to, because usually a quadrupedal, if it slips 1 leg in some dynamic motion, it may fall down, which I expect that shouldn't be the same with 6-leg robots, probably. I'm not sure.
Yes, correct. So during sub-T, there's a classic video of our robot walking about 20 meters into the cave, and it seemed to look like it slipped. That was actually a disconnection of a push rod. So one thing I like to say is that we were quite graceful in our failure. We lost a leg and we continued walking. And we didn't have that behavior active on that system where we could change from a tripod gate back to a 5+1 gate. which meant we could have kept competing, although we would have been very slow. So that again was a hardware failure. And during our testing, we had we really tried to put it into slippery scenarios, not so much like a grease slip, but like where the terrain underneath it was slipping. Yes, you slip, but stability of the platform still held up. So I was very impressed by that. Yeah, and I must add that the controller was reasonably simple to deal with.
Cool, thanks a lot.
Yeah.
Thank you very much. I think we will go to the next part of our workshop. So thank you very much for your talk. And if anyone has got questions, you can still ask questions in the chat.